Hi everyone, and welcome to a new episode of Coding Adventures. Today we're going to be exploring the game of chess. Let's begin simply by creating the chessboard. So we'll need two loops for the x and y axes, or files and ranks if you prefer. And to tell if a square should be colored light or dark, we can just check whether or not the file plus the rank is divisible by 2. Let's try running this code, and here we have our very humble beginnings. I expect I'll be staring at these 64 squares a lot in the coming days or weeks, depending how challenging this turns out to be, so I'll tweak these colors to something a little easier on the eyes. Next we'll need some pieces, and I found this nice design online, which came along with some interesting additional ideas for a giraffe, a zebra, whatever this is, and several more. I think chess is confusing enough as it is though, so I'll stick to these for now. We then need to represent these pieces in code, so I'll assign each type of piece a number, along with a number for white and black. These values could be pretty much anything, but I chose these particular ones so that if we look at a piece in binary, the 3 bits on the right will tell us what type of piece it is, and then the 2 bits on the left tell us if it has a color associated with it, which can be white or black. So let's now create an array of 64 numbers, which will be the computer's internal representation of the chessboard. These are all 0 by default, but we could place, for example, on square 0, a white bishop, and on square 63, a black queen, and whatever else we want. Behind the scenes, I also added some code for actually displaying the pieces. I'm not sure if they're obscuring quite enough of the board at the moment though, so let me fix that. Perfect. Now, instead of setting up the board piece by piece in that array, I'd like to support the standard notation called fen. Here's an example of a fen string, which might look terribly cryptic at first glance, but it's actually really simple. We start at the top left square, and here we have 7 empty spaces followed by a lowercase k, meaning there's a black king hiding in this corner. We then go to the next rank and skip 3 spaces, and here we have an uppercase n, meaning a white knight. You're probably getting the idea already, so I'll spare you the tedium of going through the rest. I've written up this little function to translate those fen strings into the format we're using, and up at the top here, I'll write out the fen for the starting position, so we can load that in. And here it is. I've also implemented some simple drag and drop behavior for the pieces, although it's not quite behaving how I'd hoped. I'll go ahead and fix that quickly, so now it's making the pieces disappear for some reason. I'm rapidly losing faith in my ability to code anything, but I have at last got it working, and I think it's looking nice. Although, of course, nothing's really stopping me from sneaking in a move like this when my opponent's not paying attention. So the first real challenge of this project is going to be calculating what the legal moves are in any given position. So, these are the indices of our squares, and from any square we can move orthogonally like a rook by adding these offsets, and diagonally like a bishop with these offsets. I'll write out those values, and then I'm going to make another little array, and when the program starts up, it's going to quickly calculate the number of squares to the edge of the board, starting from each different square and going in every direction, just so we can easily look up that information when we need it. Let's then define a little structure for holding a move, and that will just record the starting square and the target square of the piece we want to move. We can then make a list of these moves and a function for actually generating them. What we can do in here is just loop over all 64 squares and see what piece is on each square, and we're only interested in the piece if it's the right color for whoever's turn it is to move. Let's focus for now on the long-range sliding pieces. That's the bishop, the rook, and the queen. So in this sliding piece function, we can loop over the 8 different directions, and for each direction we'll also have a loop for the number of squares that exist in that direction, up to the edge of the board. Now of course, our movement might be blocked by one of our own pieces, so let's skip to the next direction if there's a friendly piece in the way. Then we can create the move going from the start square to the target square, and add it to the list of possible moves. Finally, if there's an enemy piece on the target square, we'll be capturing it, so then we can't go any further than that, and we'll need to skip to the next direction there as well. This should work for the queen, which moves in all 8 directions, but if it's a bishop, we only want to look at the last 4 directions, or if it's a rook, then just the first 4, so I've added some logic here for handling that. If we now try this out on the board, the sliding pieces should all be obediently obeying the rules. I then spent some time carefully implementing the rules for the remaining pieces, but I'll spare you a detailed account of that. So at long last, the knights are free to leap about, we can push the pawns, and I've even got the hottest new moves from the 15th century like double pawn pushes and en passant. Sacre bleu! Invader! Pawns can also become queens, or knights, bishops and rooks if they prefer, and we can castle the kings. The only thing not yet implemented, and it's kind of important, is the concept of check. Right now, if the king is under attack, you can just ignore it, so the moves at the moment are what's called pseudo-legal. The easiest way I can think of for fixing this is a little gross, but it's to take each pseudo-legal move, play it on the board, and then look at all the opponent's responses. If any of those responses is a capture of our king, we know that our last move must have been illegal, and in that way we can filter through just the legal moves. Let's put this to the test quickly. So here, for example, if I try move one of black's pawns, we can see it has no legal moves. If I select the knight though, we can either block the check or capture the queen. So now that we have legal moves, let's create our first adversary, one who plays moves completely at random.
Round 1, fight!
Okay, it turns out that playing randomly is not really a viable strategy. Just for fun though, let's pit the computer against itself. Truly a beautiful game. Now, I'd like to get the computer playing a lot better than random, of course, so experienced human players rely heavily on pattern recognition and intuition, and even when calculating concrete sequences of moves, they only really consider a tiny fraction of the possibilities, with most being subconsciously rejected as irrelevant. Programming a computer in this way is not easy. Instead, we want to play to the computer's strengths by crunching millions of possible outcomes.